Module 1, Objective 9, define acids, bases, buffers, and salts, and describe the importance of physiological pH. pH, by definition, is the negative logarithm of hydrogen ion concentration of a solution, usually characterized in moles per liter. A neutral pH is one in which you have a balance of hydrogen ions and hydroxide ions. Remember that this plus symbolism and minus sign symbolism indicates an ion, so hydrogen cation and a hydroxide anion. Pure water has a pH of 7. Anything lower than 7 is considered an acidic pH. And acidic pH solutions have a high hydrogen ion concentration and a low hydroxide concentration. Basic or alkaline pH is anything higher than 7.0, and an alkaline solution would have a low hydrogen ion concentration and a high hydroxide concentration. Within the human body, the pH of blood ranges between 7.35 and 7.45, so it is slightly basic or slightly alkaline. Looking at the pH scale goes from 0 to 14, where a neutral pH of 7 indicates a balance between hydrogen ion concentrations and hydroxide ion concentrations. If you were to take some examples here, we'll look at something extremely acidic, such as stomach acid. Stomach acid has a pH of 1, and what creates that pH is hydrochloric acid, simply HCl. On the other end of the spectrum, we have ammonia and oven cleaner and bleach. These are all extremely basic solutions, so they have a high hydroxide ion concentration. Acids are proton donors. If you remember, acidity is a solution, an acidic solution has a very high hydrogen ion concentration. If you remember, hydrogen has an atomic number of 1, so you would expect 1 proton in its nucleus, 1 electron in the cloud, and 1 neutron in the nucleus. An ion of hydrogen is created when you lose the electron. So at that point, really, hydrogen ion is nothing more than a proton. So acids are proton donors. A solute that adds hydrogen ions to a solution is an acid. An example of that would be hydrochloric acid. When hydrochloric acid is added to water, it dissociates into hydrogen ions and chloride ions. That should be negative right there. So chloride ions. Because hydrogen ions are added to the solution, it is an acid. Strong acids dissociate completely in solution. So all of the HCl's dissociate, they come apart, they decompose into hydrogen ions and chloride ions. If they do that completely in solution, then you have a strong acid. Bases are proton acceptors. Bases are solutes that remove hydrogen ions from solution, and a strong base is identified as one which dissociates completely in solution. A good example of a base would be sodium hydroxide. When you add sodium hydroxide to water, it yields sodium ions plus hydroxide ions. A strong base will dissociate. It will dissociate completely in water. So weak acids and weak bases, they fail to dissociate completely. In the case of a weak acid or base, and I'm just going to use a generic acid, I'll make one up by just calling it HX. HX will dissociate into hydrogen ions and whatever X is. So a weak acid and base, they fail to dissociate. You still have a fair amount of the parent of the reactant in the reaction. So the failure to dissociate identifies this particular random acid, generic acid if you will, as a weak acid. And the same thing goes for weak bases. And weak acids and weak bases are really used physiologically to help balance pH. Salts are solutes that dissociate into cations and anions, other than hydrogen ions and hydroxide ions. So we looked at sodium chloride, and you can see that's the sample that is on this figure. Sodium chloride is represented here in this green and purple portion of the image, and when you place sodium chloride in water, it dissociates. The sodium ions and the chloride ions, they dissociate into their individual ions. So salts are, again, solutes that dissociate into cations and anions other than hydrogen and hydroxide ions. Buffers stabilize the pH of solutions. We have numerous buffering systems within our body, and they often involve a weak acid and its related salt, which ultimately becomes a weak base. And buffers will neutralize strong acids and strong bases. An example of one of our buffering system is the carbonic acid bicarbonate buffering system. You'll learn a lot more about that when we get to respiratory system in AMP2. But it's a very important way in which our body neutralizes acids that our body produces. Superficially, we can utilize antacids towards the same effect. So antacids utilize sodium bicarbonate, this is baking soda, to neutralize the hydrochloric acid in the stomach. This is the main premise behind the over-the-counter antacids such as Tums and Rolaids. Organic macromolecules. Organic macromolecules contain hydrogen, carbon, and usually oxygen, covalently bonded. And in addition to these elements, we often find a number of functional groups that ultimately determine the chemistry. If you were to take the body and start picking it apart molecule by molecule, you would end up with 4 large piles. You would have a pile of carbohydrate, you would have a pile of lipid, you would have a pile of protein. This would be the largest pile, by the way. And then you would have a pile of nucleic acids. And these I fondly refer to as the macromolecules of life. We are somewhat familiar with these macromolecules. If you ever look at nutritional labeling, you are usually concerned about the carbohydrates, the fats, and the proteins within those. So this isn't necessarily new, we're just looking at it from a different perspective. Each of these macromolecules, macro meaning large, are made up of monomers. Monomers are subunits. In fact, identical monomers join together to form a polymer. It's almost like Legos. Lego structures, such as this DNA molecule over here on the right, is made up of building blocks. So the building blocks for this Lego structure are individual Legos. They are the monomers. Monomer refers to one, mono refers to one. And when assembled, those monomers form a polymer. And poly refers to many. So many subunits put together. So as we start working on these 4 macromolecules of life, again, they are the carbohydrates, the lipids, the proteins, and the nucleic acids. Consider the monomers. What make these macromolecules? What are the monomers of these macromolecules?